Introduce the mechanics of solids versus fluids. A solid maintains its structural integrity. Apply shear stress to a rigid block, it fundamentally holds its shape. A fluid, by contrast, yields entirely. By definition, a fluid is a substance that continuously deforms under any applied shear stress. This physical reality applies equally whether the substance is a liquid, like water, or a gas, like air. Neither can resist a shearing force. This creates a mechanical problem. In classical physics, we track the mass and force of distinct objects, but a fluid lacks rigid boundaries, making it impossible to isolate and track a single moving particle. To solve problems in fluid mechanics, we have to abandon the particle-level view. We shift our focus to a continuous volume-based system. Instead of measuring absolute mass, we measure mass per unit volume. We define density, represented by ρ, as the mass equivalent for fluids. Similarly, we replace isolated forces with pressure. We calculate a continuous normal force over a boundary area to find the pressure. When comparing materials, we often use relative density, a dimensionless ratio that measures a substance's density directly against the density of pure water. To keep our equations balanced, we standardize our units: kilograms per cubic meter for density and pascals for pressure. Converting mass and force into density and pressure gives us the mathematical tools to apply Newton's laws of motion to a continuously deforming medium. We begin with fluid statics, the study of a fluid at rest, where no internal layers are sliding past one another. This diagram illustrates hydrostatic pressure. Internal pressure isn't uniform, it varies with depth. P equals P naught plus rho g h. Rho is the fluid's density. G is the downward gravitational pull. Critically, h is the depth, representing the cumulative weight of layers stacking directly on top. This creates a strict linear relationship. For every meter you descend, the physical weight bearing down increases, causing the hydrostatic pressure to rise proportionally. The final component, P naught, is the atmospheric pressure already pressing down on the free surface at the very top before the liquid depth even begins. This equation explains why deep-sea structures must be heavily reinforced. The extreme crushing force they experience is dictated entirely by their depth beneath the surface. If you enclose that fluid, Pascal's law applies. Apply pressure to a confined fluid, and that pressure transmits equally in all directions, as shown by these equal-length pressure vectors pushing against the chamber walls. Engineering systems rely on this uniform transmission. Hydraulic lifts and hydraulic brakes use small input forces on narrow pistons to generate massive output forces across wider areas. When a solid object is introduced to a fluid, we apply Archimedes' principle. The object experiences an upward buoyant force equal to the weight of the fluid it displaces. We calculate this with the equation Fb equals rho v g. The submerged volume dictates the displacement, generating an exact upward buoyant factor countering the object's weight. A fluid at rest is predictable. Its internal forces and reactions are completely governed by the physical realities of depth, displaced volume, and the geometry of its boundary walls. Moving fluids introduce dynamics. We start by assuming a streamline flow, where fluid travels in smooth, parallel layers without irregular mixing. For an ideal, incompressible liquid like water, there is a strict physical rule. Its total volume cannot expand or compress as it moves. Conservation of volume creates the equation of continuity. Fluid moves from a wide cross-sectional area, A1, into a narrow area, A2. Because the areas differ, velocity must adjust. Entering the narrow section, the velocity vector elongates proportionally to the shrinking area. The mass of the fluid is conserved. Whatever volume enters the wide end per second must exit the narrow end per second. The flow rate remains perfectly constant. Shrink the pathway of an incompressible fluid, and it has no choice but to accelerate. A geometric bottleneck translates directly into a spike in velocity. Understanding velocity is only half the problem. To track the energy of a flowing fluid, we use Bernoulli's principle, the fluid dynamics equivalent of the work-energy theorem. Look at this control volume in a narrowing, elevating pipe. Bernoulli's equation states total mechanical energy remains constant. 1/2 rho v squared is kinetic energy. Rho gh is gravitational potential energy. Finally, P is internal pressure energy, shown by outward radial vectors. If the pipe remains perfectly horizontal,
the height does not change. The gravitational potential energy cancels out, leaving only pressure and kinetic energy. This leaves us with a critical inverse relationship. In a flat system, if the velocity increases, the internal pressure must drop in order to keep the total energy constant. Observe this velocity-pressure inverse relationship in aerodynamics. Air moving over the curved upper surface travels faster, creating a low pressure zone. Beneath the wing, slower air maintains higher pressure. These strong upward pressure vectors overpower downward vectors, generating lift. Engineers use this same principle in venturimeters. By forcing fluid through a deliberately constricted section, they measure the resulting pressure drop to precisely calculate the flow rate. Atomizers and carburetors work similarly. They blast air horizontally across a tube to lower the pressure, creating a vacuum that draws liquid upward to be dispersed. Bernoulli's principle also applies to a liquid draining from a tank, simplified as Torricelli's theorem. The efflux speed from a small hole equals the square root of 2gh. The math is identical to the equation for a solid object in free fall. A fluid exiting a pressurized column accelerates precisely like a rigid rock dropped from the same height. Bernoulli's equations assume a theoretical fluid with absolutely zero friction. In reality, perfectly frictionless fluids do not exist. Every fluid experiences viscosity, an internal friction generated as adjacent layers of the fluid slide past one another. When moving through highly viscous environments, we calculate the resistance using Stokes' law. A sphere moving through fluid faces an upward drag vector, defined by the equation F equals 6 pi eta RV. The magnitude of this drag force depends on the fluid's coefficient of viscosity, along with the radius and speed of the moving object. This internal friction is a mechanical toll. It actively drains mechanical energy from the fluid system and converts it into heat, which breaks the perfect energy conservation required by Bernoulli's equation.
Even in low viscosity fluids like water, Bernoulli's ideal model will completely fail if the velocity gets too high. This gauge measures the Reynolds number, a mathematical threshold used to predict when a fluid's behavior will break down. When the Reynolds number remains below 2000, the flow is laminar. The streamline vectors stay straight and parallel. But as fluid velocity increases, driving the gauge past 4000, the system crosses a critical limit. The smooth flow breaks into chaotic, swirling eddies. This is turbulent flow. The distinct fluid layers mix irregularly, causing an unpredictable loss of energy that standard equations cannot cleanly track. This provides a strict checklist for analyzing physical systems. Before you deploy any conservation equation, you must verify the fluid is steady, incompressible, and laminar. If it isn't, the ideal rules of fluid mechanics do not apply.